Hello and welcome to the Open Marketer. I'm Ansh and today we're going to take a look at LibreOffice Calc, which is a spreadsheet application within LibreOffice. Now, most people would know how to use Calc. It is similar to any other spreadsheet application out there. So I'm not going to teach you how to use it. Instead, I'll cover a few tools and functions within Calc that data analysts, marketers, and managers ought to know about. The first of these tools is the solver. If you're new to Solver, let's start with what it is. Normally, when you're working with a spreadsheet, you have your inputs and you have some formula or models that work on the inputs to get you to an output. In Solver, there are three sets of inputs: an objective that you want the solver to work on, constraints that tell the solver what's possible and what's not, and decision variable that the solver changes. All these go into the solver, which then changes decision variables repeatedly to finally get an optimized output and optimal inputs. So how does it work? First things first, the solver is not an AI and is basically blind until you provide it with a mathematical model to work on. You need to tell the solver everything that you know about the calculations you want it to follow to work correctly. Next, in the solver setting, you are providing three sets of inputs that we spoke about. Objectives, the single goal that you want the solver to achieve, so maximizing something like profit, minimizing costs, or even hitting a target. Then you provide a set of cells that you want the solver to change to achieve your goal. It is important here that these decision variables are connected to the objectives in some way through the formulas. Last of the inputs are the constraints. These are like guardrails that solver will operate in to make sure that the results make sense. Once these are provided, you choose the solver engine. If the problem is a linear problem, then you use a linear solver. And if it is a non-linear problem, then you use a non-linear solver. You will see this in a bit. Lastly, you run the solver. And then, most importantly, you interpret the results to see if it makes logical sense and business sense. Today, I'll take you through three solver models. Two of these are linear models. The first one is a linear product mix problem where we choose quantities to maximize profit under capacity limits, which is a classic. The second one is to allocate survey completes across cities and segment quotas to minimize costs. The third one will be a non-linear pricing model where we will choose a price that maximizes profit when demand changes with price. All right, enough talk. Let's get into the demo. So here I have a LibreOffice Calc and I have opened my workbook where I have set up the cases, and you can see that here in the Sheets tab there are three color coded sets of sheets, and I have also created some variants to the three cases that I introduced. And for each of these cases I have already set up the solver, so I'll not be setting up the solver on screen, but I will go through the different components of the solver and how you can input the different settings so that by the end you know how to set up the solver anyway. Okay, so let's get into the first case, which is the product mix case. Here the idea is to input the number of units that one should produce to maximize the profit contribution for the entire portfolio. And to make this decision, there are two sets of inputs primarily. First is the pricing, the variable cost, and thereby the margin for each of these products. And there is also the resources it takes to create 1 unit of these three products. And the resources are across machine hours, labor hours, and material units. And we have also been provided, finally, the constraints. So how many machine hours are available, how many labor hours are available, and how many material units are available. So that is the setup. And I have basically created these in different tables so that it is easier to understand. The yellow coding across the different sheets would be for the decision variables. So the solver will change these numbers, and everything else has been connected to these yellow cells using some formulas. So you can see that they have been set up here. So the profit contribution of A, for instance, is multiplication of the number of units that is produced and the margin per unit of A. Same way for B, C, and the total is basically the sum of all the three. The constraints are also done using similar logic. So I have done a sum product of the two different rows. So across all of this, if we multiply the number of units with the machine hours for each of these products and I sum them, is it more than or less than 2400? So the idea is that it should be less than 2400, and as long as these constraints are met, how much I can maximize the profit contribution. Okay, now to get to the solver, I go to tools in my tabbed interface. The other way to do this is to go in the standard toolbar and select solver from here. Either way should work. So now we have the solver pop-up ready for us. And here there are three sets of inputs, as I have mentioned before. The first is the target cell, and am I optimizing it to maximize, minimize, or to get to a value? The second is the decision variable by changing the cells, very aptly named. And then finally, we have the limiting conditions, which are the constraints. Now here, as I said, I have already entered all the required inputs, but if you were to, for example, select this, you can see E18 getting selected. I can just as easily click here, D18, and that number would change. So I'm going to just bring this back to E18. Same way, by changing the cells, if you just select this, you don't need to even click on this small icon here. You can just select this and drag with your mouse without leaving the interface at all. And the three constraints here are the B23 and B24 and B25, and they should be less than equal to, because that is the capacity in total for D23, D24, and D25. Next, we just have a look at the solver engine. So we are going to pick the linear solver. There are two of them. There is a Quine MP linear solver, which is the default one. I'm going to just keep the default. And there is also a linear solver. The non-linear solver we will pick up in the last case that we look at. So yeah, that's it. I'm going to make sure that the units that are produced are integers, which has to be true. And then, of course, it needs to be non-negative. Okay, so I think that is the basic setting that we need to do for this particular case and this particular variant. And I'm going to click on solve, and I'm going to keep the results. Okay, so here the solver came up with 66,000 as the final profit, out of which A and B have these respective profit contribution. So B is the one that has been maximized, A somewhere about 320 units, and no units of C has been allocated. That is logical, because if you see the two tables above, you can see that C has the least margin and requires the most number of resources. So not creating any units of C would make the entire portfolio more profitable. In terms of the constraints, you can see that solver has maximized the labor hours and material units, but was not able to completely reach the maximum of machine hours, which is fine as long as we are less than or equal to the logic sticks. I just want to call out, now of course these are random numbers. I have not thought much about this. There could be a possibility that with a different configuration of the decision variables, you can reach a similar profit contribution, and we will see that in the subsequent case studies. And that is mostly to do with what kind of numbers and inputs you have provided. But what we can be assured of is that the profit contribution that we are seeing is the maximum profit contribution given these inputs and given these constraints. So let's just keep that at the back of mind, and we can go into the first variant of this case, which is if there are some demand limits. Now, in the last variant, we saw that B was maximized to 1000 and A was to 320 because B has a good enough margin and requires less resources compared to A and definitely compared to C. So if I add some demand limits, like you cannot create more than, let me just reset this, you cannot create more than 700 of B, what would the final profit look like? Again, we can go to tools and we go to solver. Everything else remains the same here, E18, B14, D14. We just add these three extra limiting conditions or constraints where we are referencing the cells H2, H3, and H4, and we are adding B14, C14, and D14, which are the decision variables basically, and making sure that they don't exceed the demand limits. In terms of the solver settings, we stick to the same inputs, and we click on solve, and we keep the results. So here the profit has reduced. B has been capped at 700 and the remainder all went to A. C still has been left out. Here you can see that the labor hours were not 100% optimized, but machine hours was closer to the maximum available machine hours. So that's one way to adjust. Of course, we are adding any real world constraint that company might face. Here it was demand limits, and there could be some supply constraints as well. So let's say product C is a strategic product, or we are contractually obliged to create this product, at least 200 units of this. How would the solver use that information and adjust the units to produce to maximize the profit again? So given this new additional constraint, let's go into the solver. And I have added this additional constraint here, D14 to H8. In terms of the solver configuration, we don't change anything, still integer, still non-negative. And we click on solve, keep the results. Here as well, you will see that the profit has gone further down. We are now in 59,000. The solver first allocated 200 to the product C, given the supply constraint, and then went on to maximize the remaining available resources to achieve how much ever units of A and B can be produced. And finally, if I were to add an additional resource, for example, machine Y, and provide the constraints of the capacity for machine Y as well. So each of these row has gone one cell down. So we are looking at E19 for the target cell. We are maximizing it. Cells to change still remains the same, but I have added additional machine Y hours, and I've set the availability to 900. So that is B27 and D27. And in terms of the options, still remains the same, and we make it and we put it to solve, keep the results. So now we are down further to 56,985. Here unit A was prioritized, and we tried to use as much of machine Y as well. So machine Y almost reached the capacity, 898.5 out of 900. We reached the capacity in terms of material units, so that is why no additional unit of B was produced. All right, so that was the classic product mix and resource constraint case. Into something a little bit more marketing oriented, market research oriented, and get into sample size case. So here the idea is to define how many samples should we reach out to in 3 different cities, Shanghai, Beijing, and Shenzhen, across 2 different segments, affluent and mass, given the kind of cost per interview that numbers that we have, so that we are able to minimize the cost at the same time reaching some of these quotas that have been set by the survey team. So if I say if we need to complete at least 300 interviews, out of which 110 needs to be there in Shanghai, Beijing needs to have 90, Shenzhen needs to be 70, so about 270 should be there across these 3 different cities minimum. And then we have 120 minimum and 180 maximum for affluent consumers, and the minimum of 120 in the mass segment. Given these constraints, what would be the decision that solver would take in populating the samples across these different segments and cities? Now, from my understanding, what's going to happen, given that we have about 270 already that has to be allocated across these 3 different cities, the remainder 30 would all go to Shenzhen, probably in the mass segment, given that it's the cheapest segment and we are trying to minimize the cost. And then everything else then falls into place trying to minimize this. The other factor that you will see in this case is the jump between the 2 segments, affluent and mass, is same across all the different cities. So $4, $4, and $4 here as well. And this would mean that there are definitely multiple configurations that can reach a certain minimum target. So there's no one right answer in terms of the sample distribution. What matters is, are we able to reach the minimum cost? And we will see some of this in the later variations of this case. Let's go to solver and see what settings have been put up. So the target cell is B10. We are trying to minimize it, and we are trying to do that by changing the cells D2 to D7, which is right here. And then we have added the different constraints from B11 to B14, which is from total to the Shenzhen completes. And then we have finally mass completes and affluent completes. And affluent completes has a minimum and a maximum that it needs to achieve. In terms of the options, we still use a linear solver because it is a linear problem. And we are also making sure that, given that these are interviews, that it is an integer and non-negative in the answer. So let's solve this, keep the results. So we have reached somewhere about $3,490 as the minimum cost. As I suspected, Shenzhen, all of it went to mass, including the extra 30 that is needed to reach 300, and the remainder went into Shanghai and Beijing. Now, clearly you can see that, for example, the mass of Beijing has been left out, the affluent of Shenzhen has been left out. So you can add additional quotas and constraints to make sure that we are reaching out to all the different segments. And you will see that in the last variation, how I have added a city level and segment level quota to the mix, so that we are able to cover each and every city and segment combination. Next variation here is, many of the times premium brands specifically try to survey more of an affluent segment, in which case we have increased the affluent minimum, and the maximum is still the same. The minimum for mass still remains 120, everything else remains the same. So given this, the affluent minimum would be set up, and then from there onwards the mass will be maximized to somewhere about 140, and then the remaining city level changes will be done. So here again, the target cell remains the same. We are trying to minimize this target cell. The constraints all remain the same. We have changed the number in the cell itself, so there is no change needed in the solver settings as such. And then we do the solve, and we keep the results. So now, given that we are trying to reach more affluent consumers, we have increased our total cost from 3,490 to 3,650. Finally, if you were to, as I said, have a city and segment level quota, so let's say we want to reach 30 samples each. How does that then impact the solver answers? Here I have added these three sets of constraints, so B17, B18, and B19, and they should all be greater than or equal to E17, E18, and E19. Everything else remains the same. Let's go to options. It is still a linear engine, and we do a solve. So as I said, you can reach the same minimum levels as the one that we got here, even after adding few extra constraints. Now definitely the different cities and segments all have been covered, and you still have reached the minimum possible cost with these constraints and these inputs. So yeah, that was the solver for a city and segment sample size distribution. Finally, we'll take a look at the nonlinear model. And here we are looking at pricing and how does the pricing changes the demand and trickles down to revenue, variable cost, contribution, and profit. We are trying to maximize the profit. Each of these different cells that you see are connected to the pricing that we will set up through solver. On the right hand side, you see I have set up for all the different prices what will be the demand, revenue, contribution, and profit, and I have set up these two graphs to show you how the demand is a non-linear function and so is the profit. And here it also gives a visual way to look at the problem and guess what would be the answer. Where does the profit becomes the maximum, given that x-axis is the price? It looks like somewhere about 72 to 77, in that range the graph peaks, and so we'll see what answer does the solver comes with. So we click on solver. Here we have the target cell of the profit, that is F7, and we are changing the pricing cell, and there are just two constraints, the minimum price and the maximum price, that we have in C6 and C7 that the solver needs to follow. In terms of the engine, we are using a nonlinear swarm engine, and we want the variables to be non-negative. We are fine if it is a non-integer value, so we have unchecked that. We click on OK and we click on solve, and we keep the results. So here it looks like the solver has come up with 76.999, which is basically 77. So I'm just gonna put 77 here, and we see that we have reached somewhere about $12,841 US as the maximum profit. Now, if I were to increase the price to $80, the profit reduces. Same way, if I reduce the price to $75, the profit reduces. It's around $77 that we get the maximum possible profit with these inputs and constraints. So that was the nonlinear engine. I am only doing one variant of this, but given kind of real world examples that you can think of, you can add additional constraints as well. Like we saw in the product mix, you can think of demand constraints, you can think of supply constraints, and then add those as well in this nonlinear engine, and you can still get an answer if an answer exists. So yeah, that was the nonlinear solver in action, and that brings us to the end of the demo. If you found this video helpful, please comment and like and share it with your friends, and I will see you in the next one. Goodbye for now.